Hello, I'm James, and recently I've been exploring AI techniques in games, and here's what I've learnt. So starting with finite state machines, I set out to create my own finite state machine implementation complete with editor support in Unity. The design philosophy was to separate the design of the state machine from the programmed behaviour that the agent exhibits, in the same way that the Unity animation controller state machine separates its design from the actual animations played. So here's an agent that I created with the FSM. It's a mouse which pathfinds to a piece of cheese in the environment. Once the mouse has found the cheese, it does a celebratory jump and then circles around the cheese. If the cheese moves, the mouse will update its pathfinding and follow the cheese. The mouse is also able to react to global change in its environment, such as the time of day. Once the directional light that's lighting the scene dips below the horizon, the mouse finishes its day and goes home. Once home, it will go to sleep for the night, and when the sun comes up, the mouse can wake up and continue its day chasing cheese. There are two main ways of creating agents with my FSM implementation. There's an old way and a new way. The old way is easy to learn, but however doesn't scale well as the agent gets more complex. And the new system encourages programmers to create many small classes, each encapsulating the behaviours of a single state. These classes can be linked to the state machine through the Unity editor. Let's create a simple agent using both systems. In this scene we have a little monster creature and some foods. There are healthy gross foods and unhealthy tasty foods. In this demonstration I'll demonstrate how the FSM system can be used to create some behaviours for this monster. As for pre-existing code, there are two food types which simply implement the iFoodItem interface, and there's a mouth area which is able to detect when a food item has entered its trigger area and emits an event when it does. There's also some pre-made animations and an animation controller. So first we'll create a finite state machine in our asset browser, and now it's time to design our agent. We'll add a waiting to be fed, chewing and two reaction states, and we can link everything up. Now our design work is done, we can worry about code implementation. We'll drag and drop this FSM onto our agent in the hierarchy, and you'll see an FSM mono component attached to the agent now. We can create a new script which will contain the behaviour for the agent. We'll replace the inheritance with FSM behaviour, which gives us access to the entered state, behave, exit state and evaluate transition methods. Now we'll add our logic for the agent. And great, we can see that our agent's working in our scene. We can put some food in the monster's mouth, the monster will chew the food and then react accordingly before waiting for the next piece of food. However, the code behind this agent is poorly scalable and is already becoming a bit confusing to read through. When programming, I value small atomic classes, therefore there's a second way to interact with this system which helps programmers maintain this kind of architecture. First of all, the system makes an assumption about your project, that being that FSM agents are prefabs and any FSM related code is on the root of the game object. So now let's get into refactoring this agent to use a new system. Instead of a single main class containing all of our behaviours, we'll instead make the main class only contain behaviours and variables that multiple states interact with. With this in mind, we'll create a monster script and a script for each state. We can then add our scripts to our prefab. So in order to interact with the finite state machine, we can define our own state enter, behave and state exit functions, and as long as they are public void and accept a state as a parameter, then they will be able to interact with the system. Let's refactor the code on our agent to instead be multiple scripts rather than one. Now we can go into our state machine, select our waiting to be fed state, and you'll see three Unity events for entering state, behaving and exiting state. We'll add a callback for entering the state, drag our prefab as an object, and select the state enter function in our monster waiting component. And we'll do that for our other states. The last thing to talk about is state connections. Each state connection has a variety of ways to evaluate the transition. Handled by agent is what we used earlier and is intended to be used with the old way of interacting with the FSM. Value reference comparison I'll talk about later. And handled through interface components, which is part of the new way of interacting, and none. None is useful if you want to transition states based on some event happening, like an animation event. So as we're going to use the new system for evaluating our transitions, in our monster chewing script we'll inherit from the iTransition evaluator interface, giving us access to this evaluate transition function. It returns a ball and takes in a connection index as a parameter. Now in the editor for both connections, let's set the transition handle method to handle through interface component. We'll drag and drop our prefab into the object field and you'll see a drop down menu of all the components on the root of our prefab that inherit from this interface. So we'll select monster chewing and we'll do the same for our other reaction states. And there we go, we've achieved the same functionality, but our code is much more expressive. Finally, I'd like to talk about the value reference transition handle method. So inspired by a talk by Ryan Hipple at Unite and other materials online, I create what I call a scriptable object value reference. This allows me to create a simple ball, float or integer, which is an asset accessible from anywhere in my project. This is super useful for storing global information, such as if it's daytime in the current scene. The value reference comparison transition handle method was designed to work in tandem with this reference system. So let's demonstrate this system working by making the monster go to sleep at night and wake up in the day. I'll use this script to monitor the directional light and update a ball reference. In our monster state, let's add 3 new states to our state machine: go to sleep, sleeping, and wake up, and connect them to our waiting state. Now, to transition from waiting to be fed to going to sleep. On the second connection, we can select value reference comparison. The first field takes a value reference, currently floats and booleans are accepted. The second field is a comparison operation, and the final field is what to compare to. Let's make a similar transition from sleeping to waking up, and all the other transition will be set to none. And now we can make a go to sleep script and a wake up script, and add logic to the scripts. Finally, we'll link up the events in the UI. And now our agent is also able to go to sleep at night and wake up again. I hope this has given a comprehensive overview of the finite state machine system that I've created. This is the first time that I've created editor tooling for Unity using the new UI toolkit and really dived deep into the process. I really enjoyed creating this tool and thinking about how it could be used and what best practices I want my system to support and encourage. I think a strength of the system was that it was in part developed alongside creating an agent using the system. This allowed flaws in the systems or improvements to reveal themselves naturally, and I really like the way that you can select a component to evaluate a transition on a state connection using the new system with the drop-down menu. To be critical of this system, the way that I've used Unity events for start, behave and exit is not exactly how they were intended to be used. In this case, they're just used to provide a UI to select a function. The name of the function is then used to get the same function on the instance of the prefab via reflection. And so because the Unity event isn't actually being used and it's just a container for a function name, when you go to select the function and you see all the different functions you can select, it's actually an illusion of choice. If you selected any of those other functions, it would actually break the system because they don't match the correct signature. And so if I was to improve this system, I would create my own UI for selecting a function, similar to how a function can be selected in an animation event. Overall, I've really enjoyed creating editor utility and used these skills to a lesser extent later on with my Void implementation. I created a pathfinding system which is able to traverse a collection of nodes using a variety of pathfinding algorithms. Each algorithm is a pathfinding strategy object created as an asset in the project. This allows the pathfinding algorithm to be easily changed via the editor and even swapped at runtime. Additional to being able to customize what algorithm is used, there's also support for multiple techniques for generating the node collection. Currently, there's support for generating a flat grid. This is perfect for flat ground. Alternatively, a node collection can be created using the vertices of a mesh via centroid locations. And finally, the system has support for if a Unity terrain object is used. The terrain's height map is used to place nodes on the terrain. Additional to being able to change the pathfinding algorithm, the generation algorithm can also be changed at runtime. This system works well and is what allows the mouse in my game to move around and try to get the cheese. There are also some debugging features implemented, such as rendering the vertices of the mesh filter terrain, rendering the bounds of the box generated grid, showing the centroids, and showing the nodes of the grid in a generated grid. All of these debugging features can be added or removed by either adding or removing the grid path renderer component to the same object as the pathfinding script. If you have an agent which traverses the nodes, you can choose to inherit from the path following agent component. And now if you select the agent while it's pathfinding, the current path it's travelling along is drawn in the scene view. I followed the class resources on creating a void system, however expanded the system and added some editor functionality to allow the user to choose to make the voids multi-threaded. This increases the initial cost of the system, but allows for much better scalability. Finally, one of the topics which I visited, but not as in-depth as I would have liked to have had, is the behaviour trees. I used the following YouTube tutorials to create a behaviour tree editor, but didn't have time to actually implement any agents using this system for my game scene. It did, however, give me a great starting off point and knowledge on custom editors to create my own finite state machine, and so it was definitely worth doing the tutorial and was very interesting to follow along with. Finally, I explored goal-oriented action planning, which is a very interesting way of implementing AI, which I would definitely like to explore more into. However, I only ended up having time to follow along with some of the class content to create a basic hospital scene featuring some Go app agents. Overall, it's been very interesting to work on these features. I've really enjoyed creating systems that are used to create agents. However, I would like more experience at actually creating these agents now I've finished creating the systems. In future projects, I'll keep an eye out for opportunities to use these techniques to make convincing AI agents. Thank you for watching.